Okay, so today's lesson, we are essentially doing the previous lesson, like we're looking at compound interest, but in the previous lesson, 8.2, we were calculating the future value. So if I said you had $2,000 now, like right, using these words now or initially today, so if you have $2,000 now, you put it at some interest rate, what would you have later? But today's lesson just pretty much works backwards, okay? So if you look at this formula right here, I know it looks scary with this negative exponent, but ultimately this is just a rearranged formula from what we had in yesterday's lesson where A was equal to P multiplied by 1 plus I to the power of n. All that we have done here is just rearrange the formula and solved it for P, because this whole today's lesson is us solving for what would happen if you had, like what would be your now money given a future amount, right? So if I divide both sides by 1 plus I over n, 1 plus I over n, notice how this will cancel with this, right? So you'd be left with your formula, P is equal to A over, and then that 1 plus I over n. So, and that's like what I'm giving you right here. So the same formula, right? It's what we did in the previous lesson. It's just rearranged for P, because this whole lesson today is us calculating what is your now money, right? Like what is the money that you have today? If I tell you like 10 years from now you actually have $1 million, what did you have in your bank account before you had $1 million, right? Like that's today's lesson, okay? So in example 1, determine the present value of an investment of $650 in 6 years, compounded monthly at 6.5% per year. Okay, so it's determining the present value, right? So in this case, we are looking for P. We're looking for the money that you would have had previously, okay? So you have future value or present value of an investment of $650. So this is like what you would see, right? Like you would see like, oh, okay, cool. After 650 years, this is your A. A is, or your future value. Your A is 650. In 6 years, okay, so 6 years, that's your T. Compounded monthly at 6.5% per year. So remember from the previous lesson, you have to adjust your exponent n and your interest rate based off the compound monthly, okay? So in this case, we have 12 compounds. 12 compounds. So the problem is looking for P. Okay, so let's just set up our formula. We have P is equal to your future value divided by 1 plus I to the power of n. So we know A in our case was $650. Well, we need I now. We have I, which was 6.5%, so put that in a decimal. That's 0.65. But that needs to be divided by the 12 compound periods, okay? So if we divide that by 12, I need my calculator, 0.065, divide that by 12, that would give me 0.1254, or 5, yeah, let's leave it at that. That's good enough. Okay, and then our n in this case is we had it 6 years, so we have 6 years being multiplied by, again, our 12 compound periods. So 6 times 12, that would be 72. Okay, so now just plugging it all into our formula, right? We are looking for P, so P is equal to our $650 that we had in the future, or I guess have now. So what did we have before? 1 plus 0.0054 to the power of 72. Okay, so just carefully with your calculator, go 1 plus 0.0054, then put that to the power of 72, and then 650 divided by answer. I get a present value of 441, and again, this is in money, so make sure you have 2 decimal places, 0.08. Alrighty, So that means, what did you have initially? Well, you would have had initially $441.08. That would have been the money that you invested 6 years ago. Okay, so maybe put that note. That's how much you had. How much you had 6 years ago. And it grew to $650. That's essentially what happened. Okay, so example 2, I'm actually going to avoid this example because this involves using annuities, which is going to be a future lesson from now. So for right now, do not worry about this. And you know what? If we, I'll put a note to remember it. When we actually do the lesson for annuities, this is a great question we will come back to, okay? So we will do this in class. We will do this in class when we study annuities, okay? And I mean, just so you know why this question is different from what we are going to see in this lesson, is this whole concept of making regular payments, okay? So that's what makes this an annuity question. And I just for the sake of this video, I don't want to confuse you because annuities can be kind of difficult. So I just won't do this now, but we will look at it in a later date, okay? So let's keep going. Let's go to example 3. So Juan received $6,000 on his 16th birthday from an investment his parents made on the day he was born. If the investment earned 8.25% compounded quarterly, how much money did Juan's parents originally invest? Okay, so like you can see these words that they're using, how you approach these problems, right? It's asking for like, what was it? Like in like past tense, like what was the initial amount that you put in back in the day, okay? So we are solving for originally invested. Again, we are solving for P. P is the thing we're looking for. So we're going to use our formula, which is P is equal to A over 1 plus I to the power of n. So now we just need to figure out what A is, what I is, and what n is, right? So reading the problem, if Juan received $6,000, well, this is like what you have in the future, right? Like, so he received it. So that was $6,000. Your A is 6,000. If the investment earns 8.25% compounded quarterly, okay? So how many quarters are there in a year? Well, this is 4, right? How much money did Juan's parents originally invest? All right, so let's calculate our I. Our I is our interest rate, which is 8.25%, so that's 0.0825, and divide that by the number of compounding periods, so that's 4 in this case. So, I need my calculator, 0.0825, and I divide that by 4, and I get 0.02065, and then n is again your years that you're running this experiment for or whatever, times the compounding period, so times that 4, right? Well, what is t? Well, in this case, on his 16th birthday, right? So in this case, let's just assume that t is 16. So we have, well, not assume, but it is. So 16 times 4. So 16 times 4, that is 54. Oh, 64, sorry. My mental math, let me just double check. Yeah, 64. Okay, so now we just plug in everything we have. Our A was $6,000, so 6,000. Divide that by 1 plus the interest rate we calculated, accounting for our compounding, so 0.02065, and then putting that to the power of n, which was 64. So use your calculator, 1 plus 0.02065 to the power of 64, and then 6,000 divided by answer. So initially, the parents must have invested $1,621, and again, unit, 2 decimal places because it's dollars, 94 cents. So how much interest did the investment earn? Again, your interest is equal to your future value future minus your present, right? Or in this case, it's the A minus the P, right? So the interest is we had $6,000 in the future minus what we started with, the 621.94 equals 6,000 minus 1621.94, 4,378 and 6 cents. So that's how much money was gained from the investment. Quite a lot, actually. So it's very good to invest the money for a long time. Okay, so example 4. Amy wants to have $5,000 in 4 years. She has two options for investments. A saving account that will pay 3.5% per year, compounded monthly. A GIC that will pay 3.4% compounded semi-annually. Which investment should Amy choose? Okay, so we need to figure out, she wants to have $5,000 in her account, right? So we have to compare which one is better. Like, do we put it into the 3.5% compounded monthly? So again, we are going to have an interest rate and a end value that we have to account for by compounding, right? And then we have another one that has a different interest rate and a different compound period. So in this case, if she wants to have $5,000 in her account, right? That's her future amount. We don't know how much she has right now, and no point in here to tell us she has $3,000 or something. So when we compare, what we're really going to be comparing, which investment should she choose, right? We are comparing how much money is needed now, right? Like that's what, so if in order to have $5,000 in 4 years, one example might be you need 1,000, and then the other one might be like you need $1,500. But if you don't have $1,500 or you're nowhere close to that, well then go with the $1,000 one, right? So in both cases, so a savings account will pay, and then so let's call the savings account one. Let's call a savings account one. Let's call this option A. Option A. And then the GIC, we will call this one option B. Okay, so let's look at option A. Option A. Again, we don't know the present value. We are looking for that, right? But the future amount we want is $5,000. The interest rate given in option A was 3.5%, so it's 0.035. And we need to divide that by the compounding monthly. So in this case, we're dividing it by 12 because it said monthly, right? So we get that amount. So what is 0.035 divided by 12? That is going to be 292. And then our n, the exponent, well, in this case, it is for 4 years. So 4 years times, again, your 12 months. So that would be 48. So let's do our math for option A. So in this case, your P is equal, make it a little higher. Your P is equal to $5,000 all over 1 plus 0.00292 all to the power of 48. Okay, so put this on your calculator. 1 plus 0.00292 to the power of 48, and then take 5,000, divide that answer, and we get a present value required. You would have to have $4,346.98 in order for that to be possible. So let's look at option B. Option B. So option B, again, you're looking for present value. Your value that we want in the future is $5,000. The interest, in this case, in option B was 3.4%, so 0.0 sorry, 3/4, divide that by, and this one is compounded semi-annually. Okay, so 2, semi-annual, right? Annually. So if we do that, 0.034, divide that by 2, you get a interest rate of 0. I'm going to write it below because I'm going to run out of room on the side there. 0.017. And then your n, you have to account for the compounding. So again, it's 4 years multiplied by the 2. So you would have 8 compounding periods. So plugging it into your formula, P is equal to 5,000 divided by 1 plus 0.017, all to the power of 8. Okay, let's see what we get. So 5,000, or 1.017 to the power of 8, 5,000, divide that by answer. We would need 4,369.20. Okay, so if we look at our two answers here, so if we have this, we have 4,346, and then we have this one right here. I mean, they're pretty close, 4,369. Well, I would probably choose option A. Therefore, option A, as less money is required. Right? If she didn't have that much money, option A, less money is required. Required to reach $5,000. Or in another way of thinking about it is option A actually grows faster than option B because you start with less money and you actually make the same amount. So it is growing at this faster rate. That's another way you can think about it. Anyways, there is our homework. Okay, so I will see you in class. Bye for now.